Okay, so this is the handout that I was going to provide in our review session, and I want to just talk about a few different things. At the end of it, I had the learning outcomes from Chapter 3 and Chapter 10 for Unit 2, and this is all the stuff that we'd be covering on the exam. So what you would want to do is be able to read through this and say yes to each one of these statements, like be able to determine the empirical formula from a compound, whether that would be from mass percent or actually given the mass of each element, or if you're dealing with combustion where you produce carbon dioxide and water and being able to determine the empirical formula from that. Be able to determine the molecular formula, right? And remember, we need the molecular mass in order for us to be able to identify that. If we don't have the molecular mass, there's no way we can determine the molecular formula. A lot of these other statements have to relate to mole relationships, like dealing with molar amounts between elements and looking at something like Fe2O3 and being able to say from that, right, we would have 2 moles of iron would equate to 3 moles of oxygen, or 2 moles of iron would equate to 1 mole of iron 3 oxide, Fe2O3, just being able to relate within that. The fourth one is looking at the molar amounts in reactants and products from a reaction. Okay, so again, this is looking at a balanced chemical reaction and using the coefficients as the molar ratios. Okay, and hopefully we're fairly comfortable with doing that. It's things that we've been using and identifying a lot over this unit. Real important here is looking at limiting reactants for reaction. And one important thing that we should be able to do that's related to limiting reactants is looking at this idea of limiting reactants with gas reactions, because kind of combining Chapter 3 and Chapter 10. And I have some example problems that I'll mention in a second that kind of help us connect those two pieces. So looking at limiting reactants, right? Limiting reactants, and kind of on this next one is understanding kind of the concepts behind limiting reactants and excess reactants, and us being able to identify these and be able to determine, well, what's limiting, what's excess. Important way that we identify, do we actually need to do that, is are we actually provided the amounts of 2 or more reactants. Okay, well, if we're only provided the amounts of only one reactant, well, we know that it's going to be our limiting reactant, the one that's going to be fully consumed. But if we have the amounts of 2 or more, we got to figure out which one is actually going to be consumed fully first, and that would be our limiting reactant, the one that limits the amount of a product, and then the excess reactant, the reaction that we have actually extra of. The next one is dealing with this idea of actual yield, which is determined experimentally. Theoretical yield, which is calculated from our limiting reactant, and then our percent yield that simply relates those two. The next few are dealing with gases and how we relate those, and so being able to understand what is gas pressure, what is that caused by, whether it be in a container or atmospheric pressure. It's dealing with this idea of collisions and how those collisions lead to a force exerted on the wall of a container or in the atmosphere. And then the rest of these are kind of dealing with laws, right? These here are dealing with laws of our gases that we'd be dealing with, whether they would be relating the pressure, volume, and temperature at a constant amount of gas, right, which would be our combined gas law, or dealing with the ideal gas law, and whether that would be simply for a sample of gas, okay, so looking at pressure, volume, amount, and temperature for a single sample, whether that be, I have 15 grams of oxygen at 250 torr at this temperature, what would be the volume that would occupy, okay? And then using the ideal gas law in reactions, so this is real important. Something that I want to mention that makes it that we kind of get lost in when we're dealing with gaseous reactions and how that deals with the ideal gas law is that, let's say we have this reaction here. Okay, and each of these are a gas. Okay. Actually, let's make it so this one here is a solid. Okay, so reactant A is a solid. So in this reaction, if we're going to go from, the amount of A to the amount of B, okay, what we'd see is that there's various ways that we can do that. So what we've done previously is we can say, well, I have the mass of A, and I'm going to convert that to the moles of A, right? And so we would use our molar mass. And then we could go ahead and go to the moles of B, and that would be using our molar ratio from our reaction. And then we can go ahead and maybe go to the grams of B, and then again using the molar mass of B. Okay. Well, when we're using gases, we typically don't measure the mass of gases, right? We use measurable quantities like pressure or volume or the temperature of that gas. So what we have the opportunity to do is we have the opportunity, instead of using molar mass to relate moles amount with something, what we would do is we would say, well, we also have the ability to use the ideal gas law to relate pressure, volume, amount, and temperature. Okay, so that means we have the ability to record a volume of a gas and know the amount of it and know the temperature, and then be able to predict the pressure that that would exert. Okay, or if we knew the temperature and the volume and the pressure, we then can figure out, well, how many moles am I actually reacting here? Okay, so we can treat the ideal gas law as, quote unquote, another conversion factor, where we can go from measurable quantities, pressure, volume, and temperature of a gas, to the number of moles. Okay, just like we use molar mass to go from mass to moles or moles to mass. So we just see it's another tool in our tool belt of looking at molar relationship in reactions. So real important of how we can use that in chemical reactions. And then these last two here, 13 and 14, going back to our learning objectives. 13 is conceptually related to what makes something behave non-ideally. So what is a real gas, right? Looking at temperatures, right? Where we're looking at really low temperatures and pressure conditions that cause us to deviate from ideal gas behavior. And that's really high pressure conditions. And we should know why that's the case and be able to understand it. And the 14th is dealing with this idea of the kinetic molecular theory and relating that to the explanation of why, right? Looking at the gas law relationships, we should be able to use Boyle's law, pressure and volume, and be able to say why are those two inversely related to each other using the kinetic molecular theory. Okay, it's not just saying, well, as you increase pressure, volume decreases at constant amount of temperature, but be able to explain why using the ideas of collisions and how that relates to pressure, how temperature affects the movement of the particles, etc. Okay, so those are our learning objectives, and those are just some kind of high-level things that we should be aware of as we're looking at this unit and preparing for the exam. In addition to that, I also provided us kind of the tools for Unit 2. Okay, and so these are conversion factors, right? We talked about this, mass to mole conversions. We're going to use the molar mass. We're dealing with moles and the actual number of the foundational units, like atoms or molecules or ions. That would be using Avogadro's number. Mole to mole ratios within a compound. Okay, so that's using our conversion factor, are those subscripts there, right? 4 moles of B for every 2 moles of A. And then conversion factors within reactions, and using our coefficients here, 3 moles of B for 2 moles of A in our reaction here. Again, we should be familiar with identifying limiting reactants, but also conceptually understanding what they are. And the rest of these are just simply relationships, right? Percent yield, how that relates experimental and theoretical yield, combined gas law, remembering that the only unit that we have to make sure that we restrict our measurements to would be Kelvin, because this Kelvin temperature is only directly related to our pressure volume. Our temperature, excuse me, is only directly related to our pressure and volume in units of Kelvin, our absolute zero temperature. And then using an ideal gas law, right, as a reminder, look at the gas law units that were provided, liters, atmospheres per mole Kelvin, and that tells us what pressure units we need to use: atmospheres, volume, liters, moles obviously for N, and temperature in Kelvin. Just in case we forget, that kind of reminds us of that. And then Dalton's law on partial pressures relates the individual components of a gas mixture. Okay, so remember, this only applies if we're dealing with a gas mixture, and then that gives us the ability to relate our mole fraction, right? Just think about it as like a mole ratio, which is the number of moles of a component. So maybe if we're dealing with the partial pressure of A here, that would be the moles of component A, whatever that would be, carbon dioxide, nitrogen, etc., divided by our total number of moles, and then that equals the partial pressure of A to the total pressure. Okay, and those are our tools that we have for Unit 2. Okay, I also have some problems that I've posted solutions to for this review session. As you go ahead and look through these, that I have them worked out piece by piece and how you identify that. I just want to talk just real quickly about some important things with these and some things to be aware of, right? So dealing with mass percent number 1 of aluminum sulfate, right? So here we're dealing with a theoretical mass percent, because we are not measuring the mass of aluminum, mass of sulfur, mass of oxygen here. We're just told it's aluminum sulfate. How much sulfur would we have? And the way that we would look at that is we would say, well, if I have 1 mole of aluminum sulfate, how many grams would I have total? What would be my mass total? And then what would be the mass of the sulfur in that 1 mole? Okay. Number 2 is looking at the number of atoms of oxygen in our aluminum sulfate sample. So we would go from 54.5 grams of aluminum to moles of aluminum, and then we would go to moles of our oxygen, and then finally we would want to go not necessarily to the mass of oxygen, but to the number of actual oxygen atoms related to this 54.5 grams of oxygen. And remember this mole ratio here, right? That is from our compound formula. And looking at, we have 2 moles of aluminum for every 12, right? 4 times 3, 12 moles of oxygen. That relates that. Number 2 is dealing with empirical formula. So we're dealing with something that has carbon, hydrogen, and oxygen. And we're given the mass percent of carbon and the mass percent of hydrogen. Well, we aren't given the mass percent of oxygen, but we know that there's only 3 pieces. And so we know that carbon plus hydrogen plus oxygen is going to equal 100%. So we can identify the mass percent. Now remember, when we're dealing with empirical formulas, we would need to be able to identify our mole ratios. Right now we just know percent by mass. So what we would do is we need to go from mass percent to actual masses, right? And if we're dealing with percentages, the easiest way to do that is just say we have 100 grams of our sample. And so that makes our percentages equal to whatever mass we would have. So we'd have 63.2 grams of carbon, 5.29 grams of hydrogen, etc. And then we would go ahead and determine the moles of carbon, hydrogen, and oxygen in our 100 gram sample, and then find our lowest whole number ratio, which would be our empirical formula. That's the definition of our empirical formula. And then number 2 sub 2 here would be determine the molecular formula. The only way we can do that is if we actually had experimental data that told us what the molecular mass is. Okay, and I provided that experimental data in the handout. Okay, so if we're asked to determine the empirical formula, right? The only way we know the empirical formula is if we have data on the molecular mass. Okay. Number 3 is dealing with stoichiometry. propane gas reacting with oxygen, producing carbon dioxide and liquid water. So in this one, right, we're going to balance out our chemical reaction here. And then number 2 says we have 1.2 grams of propane. It's added to 350 milliliters with 5.25 atmospheres of our oxygen gas at this temperature. So that means we have a temperature, we have a pressure, and we have a volume of our oxygen gas. So what that means is that we have the amounts of 2 of our reactants. Okay, so that means that we need to determine what is our limiting reactant. Okay, and the way that we determine what our limiting reactant is by going ahead and saying, well, if I had all of my propane react, how many grams of carbon dioxide am I going to get? The reason why I chose that product is because that's the one we're looking for the theoretical yield of. And then I have the volume, pressure, and temperature of oxygen, so I can go ahead and go for that and determine the number of moles of oxygen using my pressure, volume, R and T, right, using the ideal gas law. Well, then I could go ahead and use that to find out how many grams of carbon dioxide would I form. And remember, the one that has the lower mass, that tells us that's the reactant that's limiting the formation of our product, and that would be our limiting reactant. Okay. Our final portion of this problem is looking at if we had 100% yield, so our theoretical yield would equal our actual yield, what the partial pressure of each gas present in the container would be. Okay. Well, if we go ahead and we look at our reaction, we know that we have a gas as a reactant, another gas as a reactant. We're producing a gas as one of our products, okay, and then we're producing water. So the total pressure is going to be whatever gases we have present that are left over. Okay, so we have propane, we have oxygen, and we have carbon dioxide. So we don't think about water because it is a liquid, right? It's not going to contribute a pressure here. So now if we're looking at identifying the partial pressure of each of these, well, one of these, I'm not going to tell us which one right now, one of these is going to be the limiting reactant. Okay. Well, if that's a limiting reactant, then let's say, for example, whichever one is limiting reactant, maybe it was oxygen, that wouldn't be there, right? All of the oxygen would have reacted away, it would be gone. And that would have gone down to produce some amount of our carbon dioxide. And so then we have to figure out, well, if this is excess, how much excess do we have? We don't still have 1.2 grams of propane. How much do we have? And so we have to look at, based upon, I'm just assuming here and saying, I haven't worked the problem out here, but I did in our answer sheet that, if this is limiting, how much of that propane would be left over? And that would contribute to the total pressure. Okay. Number 4 is dealing with the molar mass of a gas. And so here we have the density of this gas, a temperature, and a pressure. Okay. And so our first thing that we're asked to do is determine the density of when the temperature is increased and the pressure is increased as well. Okay, so we didn't add anything to this gas. We're looking at the density change. So what we can do is we're saying, well, we're just changing temperature and changing the pressure. So what we could say is, well, what if we have 1 liter of this gas? Okay, that would be our V1, and we have our P1 here, our T1 in Kelvin equals our T2 here, our P2, and then we would say, well, what's the new volume? Okay. Well, once we identify the new volume, we could go ahead and calculate our new density as being still at 1.14 grams, right? Because we didn't change the amount in this 1 liter before we expanded it, divided by what our new volume is. And that would tell us our new density in grams per liter. Number 2 is looking at the molar mass of this gas. Okay. Well, in order for us to identify the molar mass, we need to know the number of grams divided by the number of moles. Okay. Well, if we already know the density is 1.14 grams per liter, well, what we can do is we could say, well, what if we go ahead and have 1 liter? Well, that means that our mass would be 1.14 grams, And so we need to figure out, well, how many moles would we have in this 1 liter? Well, now we know, we've identified and said we have a volume. We now know that that corresponds to a temperature of 22.0 degrees Celsius. And we'd want to convert that to Kelvin. And we have a pressure of 750 torr. Okay, and that was provided, that's the information that was provided up here. Okay, and again, we want that to be in atmospheres. Well, we could go ahead and determine our number of moles using the ideal gas law. We have a pressure, volume, temperature, and we know R. And then we could go ahead and plug that in for our number of moles to find our molar mass. Okay. And then number 3 is looking at what the identity of this gas is if it's a pure element. So we kind of match up our molar mass to the closest pure element. And just don't forget, some of these pure elements do exist as diatomics. So we need to identify, well, which ones could possibly be a gas that's a diatomic that would match up here. And then the final problem that I had for our review session was looking at if we have 10.5 grams of helium in a 1 liter container at that temperature. So according to the ideal gas law, determine the pressure that this would exert. Okay, so that's simply kind of a plug and chug here where we have nRT over V. We have our volume, we have our temperature already provided to us in Kelvin, and we have a mass and the identity, right, which we could easily then convert to the number of moles of helium. And so now we have N, R, T, and V. And we can go ahead and solve for the pressure. So that would tell us what it would be if it followed the ideal gas law. And so what we're told here is that the actual pressure of this gas is 1.55 atmospheres. Okay, so we want to explain why this differs from the ideal gas behavior. Okay, so we're thinking, why does it deviate from our ideal gas behavior? Okay, and so what I'll tell you right now before we do this calculation is that this is lower than the ideal predicted pressure. Okay, and so we want to think, well, what is causing that, right? Well, if it's lower, that would be, we would have a lower number of collisions that would be prevented for comparison to an ideal gas. And so we think, well, if that's the case, we have a lower number of collisions, what's causing that, right? And so just remember what's different here, what would cause this deviation. We're sitting at a really low temperature, okay? And so we see this, we start to see where our gases begin to interact with each other. Well, if they start to interact with each other, that deviates their path that they would have, and so the number of collisions with the wall would be less, and so then our pressure would be less than we actually predict. Okay. So this was just a real quick overview of the questions and topics that would have been discussed in our review session. Again, I've posted the solutions to this, so you can go ahead and look at that. If you have questions, feel free to contact me. But happy studying, and I will see you all in class for the exam.